Now we're going to take a look at the effect of the substrate on the E2 reaction mechanism. Recall that it's this transition state that we're interested in, and so we need to think about factors that will help to stabilize this transition state. And the first feature that we're going to investigate here is the developing pi bond. Let's first talk a little bit about alkenes and their relative stability. And what we want to note is that when you have more carbons on an alkene, particularly sp3 carbons, you get a little bit of an electron donating effect from these guys because of the difference in the %S character. And this electron donation actually stabilizes the forming pi bond. The bottom line for us is that more R groups on an alkene equals a more stable alkene. Here is an alkene that has 4 such R groups on it, and we call this the tetra-substituted alkene, and this is going to be the most stable type of alkene that you can form. Next in line is when you have 3 R groups and only 1 proton, and this is a tri-substituted alkene. It's next in line in terms of stability. Then we get to the di-substituted alkenes, and you see that there are a couple of different arrangements that can take place. So you can have the trans isomer with the 2 R groups on opposite sides. You can have the cis isomer with 2 R groups on neighboring carbons but on the same side. And then you can have the 2 R groups situated actually on the same carbon. In terms of stability, all 3 of these are less stable than a tri-substituted alkene. But of these 3 di-substituted alkenes, trans is the most stable, and then the cis, and this is called the geminal alkene, they're going to be approximately equal in stability. So we can insert these into our scheme. Recall that tetra is the most stable, followed by tri-substituted. Then we have the trans di-substituted, and then the 2, the cis and the geminal di-substituted variations. Next, of course, you would have only 1 R group, and that would be a monosubstituted alkene. In terms of stability, the monosubstituted alkene comes in below any of the di-substituted variations. And then finally, you have the simplest alkene where you have only hydrogens on the alkene. This is ethene, where there is no substitution, and this would be the least stable of all. So here's the full scheme from most to least stable. If we have an alkyl halide that has R groups at all of these positions here, you will end up with the most stable, the tetra-substituted alkene product. But the only way that this is possible is if you start with a tertiary halide. A secondary halide that looks like this would yield a tri-substituted alkene product. And of course, a primary alkyl halide that looks like this with R groups at the beta position would yield a di-substituted product. As a side note, methyl halides cannot undergo E2 or E1 eliminations. There's no beta proton to eliminate. So because of the difference in alkene stability, it turns out that E2 eliminations prefer tertiary halides as the substrates because those yield the most stable alkene product. And primary halides are going to be the worst substrate for E2.